Hi, in this video we will explain the Kruskal algorithm and how it works. So, Kruskal algorithm created by Joseph Kruskal in 1956 and one of the most important algorithm in graph theory. So, Kruskal algorithm is used to find the minimum spanning tree or MST in a graph. What is MST? MST connects all the points or nodes in a network with the lowest possible total edge weight without forming any cycles. Like, imagine you want to connect houses in a village with electric wires and you want to use the least amount of wire possible. That's what Kruskal helps with. And how Kruskal algorithm works? Kruskal algorithm is greedy, meaning it always picks the lowest cost edge available. It starts by sorting all the edges from smallest to largest, then it picks the smallest one and keeps adding edges as long as they don't form a loop until everything is connected. So what is the time complexity of Kruskal algorithm? It is OE log E. That's because it needs to first sort all the edges, which takes log the log time, then use a union find structure to check if adding an edge would make a loop. It works very efficiently in sparse graph where the number of edges is not too high. So to summarize, Kruskal algorithm is fast and reliable way to connect all parts of a network with the least total cost, making it useful in real-world problems like internet, cabling, road planning, and electric grids.
Imagine you are setting up inter-branch travel connections for a nationwide travel agency. You need to connect all the branch offices at the lowest possible setup cost, ensuring that every city is reachable from any other but without building redundant or circular paths. We're going to follow this Kruskal's algorithm step-by-step process. We have to sort all the routes in ascending order of cost. Select the lowest cost route that doesn't form a cycle. Repeat until all cities are connected or budget is reached, and skip blocked or restricted routes. Since we have constraints and priorities, the number one is block route for Manila to Davao, and the budget limit is 50,000, and the requirement is to have Zamboanga connected from any other vertices or cities. Here we have a total of 6 vertices or cities, namely Manila, Cebu, Davao, Iloilo, Zamboanga, and Baguio. On the right side, we have the table of the edges, the routes and cost of travel setup. Following the step-by-step process of Kruskal algorithm, we're going to sort all the edges by ascending order by cost, arranging all the connections based on their setup cost from lowest to highest. The second step is to start picking the lowest cost route that connects two different cities or nodes. But before adding the route, we're going to check if the two cities are already collected indirectly. If yes, we're going to skip it to avoid a cycle. But if no, we're going to add the route and connect them. And we're going to repeat until all cities are connected. Here we have labeled or colored the line for the restricted route for Manila to Davao as a red, since it's on our constraint and restriction. Second is we will choose the lowest cost route, which is the route for Manila to Baguio, with a travel setup cost of 6,000 pesos. So we're going to check if it has we're going to check if these two cities are already connected indirectly. Since it's not, we're going to add the root and connect them. In this case, to um, we're going to use a green colored line for the um, added root in the minimum spanning tree. Then we'll continue the process. The second lowest cost route is the Iloilo to Cebu with a travel setup cost of 7,000. We're going to check if these two cities are already connected indirectly, and because it's not, we're going to add the route and connect them, like what you're seeing in the screen. The third lowest cost route is the Cebu to Davao with a travel setup cost of 8,000. Since these two cities aren't connected indirectly, we're going to add the route and connect them. Then we'll continue the process. 9,000 for the route of the Davao to Zamboanga is the fourth lowest cost route. Since these two cities aren't connected indirectly again, we're going to add the route and connect them. The other lowest cost route is the route for Manila to Iloilo with a travel setup cost of 10,000 pesos. We're going to check if these two cities are connected indirectly. It's not connected, so we're going to add a route and connect them. This continue the process. 12,000 pesos for Manila to Cebu. We're going to check if the two cities are connected indirectly, and it's connected. Because if we're going to add this route, it will form a cycle, which is not advisable, or it's restricted in the Kruskal algorithm. So we're not going to add this route. Then next one is the Baguio to Iloilo route with a total setup cost of 14,000. If we're going to add this route, it will form a cycle. So we're going to skip it. The next route is the Iloilo to Zamboanga with a travel setup cost of 15,000 pesos. And it will form a cycle if we're going to add it. So we'll skip this part. The last one is the Baguio to Zamboanga route with the travel setup cost of 20,000 pesos. And if we're going to add it, we will form a cycle. So again, we'll skip it. Since all the route, all necessary route are connected and there's no more route to add, we're going to show the final minimum spanning tree for that scenario. And this is our final MST with a total setup cost of 40,000. We also have another way to track which cities are already connected by utilizing the union find table and Kruskal's algorithm. Before adding an edge, it checks if the two cities belong to different sets or not connected. If they are connected, adding the edge would create a cycle, so it's skipped. If not, the algorithm unites their sets to show they're now connected. This process ensures that the minimum spanning tree includes only edges that connected all cities without forming cycles, minimizing the total cost. We have a table before and after the Kruskal algorithm. Before, the total cost is 119,000. But after utilizing the Kruskal's algorithm, we have a total cost of 40,000, which is lesser than the budget limit of the travel agency, which is 50,000. So, using Kruskal's algorithm to find the minimum spanning tree for the travel routes between cities significantly reduces the total travel setup cost. While the original network includes all possible routes with a combined cost of 119,000, the MSC selects only the essential routes that connect all cities without creating cycles, lowering the total cost to 40,000 pesos. This represents a cost savings of 79,000 pesos. This optimized selection ensures that every city is connected with the minimum necessary infrastructure, eliminating redundant or expensive routes while maintaining full connectivity. Therefore, applying Roscoe's algorithm provides a practical and efficient approach to minimizing travel setup costs in network design.
Now, let's evaluate Kruskal algorithm through measurable performance criteria. We use three main metrics: execution time, total MSD weight, and memory usage. To provide comprehensive assessment, we tested the algorithm on both synthetic graphs and real-world data scenarios, like our simulated travel agency network. The results showed that Kruskal's algorithm performs exceptionally well on sparse to moderately dense graphs. It consistently produced lower total MSD weights and scaled better than Prims when dealing the edge heavy graphs. This makes it ideal for networks where connections are limited or costs vary significantly. What makes Kruskal algorithms stand out? It's easy to implement, especially when using disjoint set data structures. It shines in scenarios where the full list of edges is known ahead of time, and it delivers excellent performance on sparse graphs. With union find optimization, its efficiently increases dramatically, but it's not without limitations. In dense crops where edge count is very high, sorting all the edges becomes computationally expensive. Also, if union find isn't optimized, performance can drop. Finally, in graphs with a high number of vertices, Prim's algorithm may outperform Kruskal. Let's summarize. Kruskal algorithm is a powerful tool for building minimum cost, fully connected, and cycle-free networks. In our travel agency simulation that help us connect all cities within budget, avoiding block routes and ensuring Zamboanga was included. Looking at the big picture, Kruskal algorithm is efficient and execution time, economical and memory usage, scalable especially for edge-heavy or sparse graphs. This combination makes it a reliable choice for network design, especially when flexibility and cost efficiency are priorities. In conclusion, Kruskal algorithm is a simple, reliable, and practical approach for real-world problems. Whether you're designing a telecommunication network, planning transportation routes, or optimizing infrastructure, its balance of efficiency, and simplicity, and adaptability makes it a key part of the algorithm toolkit.
So the overall discussion, the Kruskal algorithm effectively builds a minimum spanning tree or the MST by connecting nodes using the lowest cost routes without forming cycles. In real-world simulation, such as a travel agency connecting multiple cities, the algorithm consistently minimizes total costs while ensuring complete connectivity. The core of the algorithm follows this procedure. Start picking the lowest cost route that connects two different cities or its nodes. Before adding a route, check are these two cities already connected indirectly? If it's a yes, keep it to avoid a cycle. And if it's a no, then add the route and connect them. Repeat this process until all cities are connected. This approach ensures that the final network includes only the essential connections with no loops or unnecessary expenses. Performance assessments showed earlier that the Kruskal algorithm to be efficient in terms of execution time, memory usage, and scalability.
especially in a sparse or edge-heavy graphs. It performed better than Prim's algorithm with a full list of edges was available. However, it may be less optimal in dense graphs without an optimized unifying structure. So the Kruskal's algorithm is a simple, reliable, and practical method for solving real-world problems involving cost-efficient and cycle-free network construction. So these are the references. Thank you.